What is up, everyone? It's the boy Python Sean. I don't know if you guys can tell by my voice. I'm not feeling well, and I haven't recorded a video in so long. I've been sick for the past 2 days. I'm feeling better now. I've been taking a lot of medicine, resting, trying to get better. And yeah, gonna be grinding more Leetcode. So sorry I haven't posted in a while. My friend's birthday was actually 3 days ago, or let me check. Yeah, 3 days ago. And it was really really fun. We played a lot of FIFA, Naruto. It was really really fun. So I haven't done Leetcode in 6 days, but it's fine. Let's continue doing Leetcode. Keep on improving. And yeah, today's question. So I do owe you guys a lot of questions because I haven't done it in such a long time. We're gonna try and do the last question of linked lists, and then we'll head to trees. I don't think I think I did this like a while ago, but yeah, we'll do them again. So I owe you guys 3 questions, so we'll just do them real quick. Yeah. So but yeah, you guys. I hope you guys are excited. Oh, why is that there? Oh, yeah, I think I was also trying to record a video. I last recorded this November 11th. We're currently November 28th, so it's quite some time since I've done it. Honestly, don't even remember this question that much, but I think I still remember the intuition of what we're trying to do. So yeah. Also, Advent of Code is also coming up, which is really interesting. I'll try and get some Advent of Code questions done as well. A lot of videos to be done, a lot of things to learn. I'm really excited. But yeah, let me know if you guys what else you guys want me to do. Please remember to put it in the comments and like the video and share with other people who also are doing like coding. Another thing I had the honor of in my university, let's say Kent to corporate. I was one of the panel speakers. Instagram. I don't have Instagram, but I was one of the panel speakers, and I was speaking. I was speaking for the basically helping them break into tech, and that was one thing I was doing as well. This was on the 26th. So yeah, really really interesting stuff. This week has been really busy, and yeah, I've also been doing a lot of stuff with AWS, learning about system design and development, and yeah, it's going well so far. And yeah, okay, so enough of the waffle. Let's actually start in this question. Design a data structure that follows the constraints of the least recently used cache (LRU). Sorry, this cold is really annoying. Okay, so this LRU cache has a constructor, and this will initialize a cache with positive size of capacity, and then we need to create a function get that can return the key if it does exist. Otherwise, it does return -1, and put, which updates the value of the key if it does exist. Otherwise, it just adds it to the cache. If the number of keys exceed the capacity, we want to kind of remove the least recently used key. The functions get and put must run on constant time average, time complexity. So the idea is in this problem is that we do want to be able to put an element into a hash map and get an element from a hash map in constant time. The problem is with a hash map, if you are putting an element or you get an element, that is constant time, because how a hash map works is a hash map has an array of a fixed length, right? And when you have this fixed length, as you're adding an element, you're actually hashing. You actually create a hash for that specific element. I don't know if you notice in Python when you try to maybe put a list into a hash map, because it has to be immutable. It can be changed, because then if it changes, then the hash might be different. So you have to have something that isn't going to a mutable object. A non-mutable object, which you can create a hash, and then that hash you can actually mod it by the length of the array, and then kind of index it into the array. There are typically two ways you can do this. You can use open addressing or chaining. The one I'm very familiar with is one I always used in university is chaining, where you essentially use a linked list, because it's possible that two elements that are non-mutable could give you the same hash and index the same position in the array, right? So how do you handle these collisions? And that's where you can either use open addressing or you could use chaining. I don't know much about open addressing. probably something I do need to learn, but I do know about chaining, where you essentially use a linked list and traverse that linked list until you do find it. Yeah, so that's how a hash map works. So these operations are in constant time, but the problem then arises as to when we want to evict an element. Well, when you have a hash map doesn't really tell you what the least frequently used element is. You could, in theory, kind of like update the map every single time you do a put or get, and like. But even when you do want to evict, you have to still traverse the map and find the element with maybe the lowest count, the lowest use count, and then remove that. And that again is in constant time, average time. In fact, it's linear time because we have to scan through the entire map. So the idea of this problem is that we're actually going to create two nodes. These nodes are going to be called the LRU node and the MRU node. So the LRU node is going to be the least frequently used node, and the MRU node is going to be the most recently used node. And I said least frequently used, I meant to say least recently used. So how does this work? When we want to put an element, we're essentially gonna have a hash table. It's going to be the same idea of the hash table. Let's say we're trying to put 1. So we're going to put 1 as the key. So the key is going to be 1 here. And the value is actually going to be a reference. So we're going to have a reference to a node, an actual linked list node. And this node is going to be inserted into this this linked list, like this W linked list actually. So when we have this 1 here, we're going to make it reference the actual node in the linked list. So when we are inserting, we can do two things, right? When you insert a node, it's the least frequently used. So we actually want to put that new node, this new node here, right? So we can put a node here, and then you can zoom. It's a W linked list, so it also has a prev and a next. It's going to be a bit weird to like show how this works, but you can think about it that when we are inserting a node, that is when we can. But the question is, you might be thinking, how are we going to actually insert them into the W linked list? This has to be in constant time, so we can't do any like traversals. That's the main reason why we have this nodes, to help us with the insertion and removal, because essentially for the inserting, we're just going to be changing pointers, right? Which is constant time. No matter the size of the list, it'll always be the same time complexity. That's the idea here with the remove. And then for the adding, we're actually just going to add. So for the adding, we just like put that right in the LRU, in the least frequently used. But then when we're actually getting the element, when we actually do a get, or an update, even like if we are updating, that does count as it kind of counts as using it. So we need to actually remove this node from the list, right? And we essentially need to put it again at the front. So wait, let me think for a second. Yeah, so when we are putting and getting, we need a way to kind of this node can't be in the least recently used anymore. So instead, it's going to be added. So it's going to be behind this node. So it's going to be here. So it's no more going to be here anymore. And how do we do this? Remember, because we have a W linked list, it's very easy to like update these pointers. And that's like the kind of key idea. I will show you what I mean in the code. I don't even know how this is going to look. This is just going to be based on my intuition and understanding. But I will show you what I mean essentially when I start writing the code. So let's start the basics. So we do need a way to kind of capture this capacity. For the size of we are going to be using a hash map, as I did say before. So we do need a way to kind of capture the capacity. And the capacity is going to be passed in the constructor. So that makes things a bit easy. Once the linked list, once the LRU cache is created, we need to actually create the LRU node and MRU node. So we're going to create the LRU node, which is going to equal to a node. So we actually do need to define what a node is. So above here, we're actually going to create a new class called a node. A node is going to have a constructor, just like the LRU cache. I haven't coded in a while, so I'm a bit rusty here. But essentially, this is going to take in a value. You can take in a value, or it doesn't even have to take in a value, it's fine. oh, let's make it say value is fine. We can make a value, so this will take a value, and it actually has a self next and a prev. This is how you implement a W linked list. Essentially, all nodes have a next and a previous pointer, and they store the value in which they were assigned in the constructor. Okay, so what are we doing now? We need a way to kind of store, create our LRU node and our MRU node. So these are going to be nodes. This is going to be a node. Let's do it like this. And because these are not going to be really used, I'm just going to pass in -1, right? Well, they're never going to be used, so it's fine. In theory, yeah, we'll just pass in -1, it's fine. So these are our MRU and LRU nodes. And the next thing we actually do need is that we need to create our hash map, which I did say we needed. Right? So now that we have this hash map, what are we trying to do? So let's start with the puts, right? We actually need some helper functions, because what do I mean? Because when we are, for example, putting an element into the hash map, what are we doing? Well, we're essentially putting the key into the hash map, and its value is going to be that node. So we actually need a way to insert a node and delete a node, because when we're doing the delete is when we kind of run out of capacity and we need to remove the least recently used. So we're going to create two new functions here called remove, which also takes in a node, because remember, we can't iterate through the list to kind of remove it. We need a way to kind of remove a node in constant time and add a node in constant time. That's why we have these two nodes, right? So we're just going to be modifying them in a very simple way. So then we're also going to have our add node, node. I think I'm going to make this more intuitive to node. This also takes in a node, and this is going to do some work, right? So when we are inserting when we are like putting an element into the LRU cache, we need to first check if the key is not in the hash map. Then we essentially need to create the node, right, and then put it into the hash map. So what are we doing here? So we would actually create a new node. So we need to essentially create the new node, which is going to equal to a new node, which is going to store the value being stored that's been trying to be inserted, and we want to basically say the map at the key is going to equal to this new node, right? Sorry, it should be new node, right? So I guess, yeah, so we can just do that instead, right? What was that? Okay, so if the key is not in the map, then we essentially want to kind of create a new node and then put that in the map. If the key is in the map, what do you want to do? We kind of want to update the value at the new node. So so instead of that, let's actually yeah, so let's do that and then do this. But if it's in the node, we want the self.map else self.map a key.val is going to equal to the new value, because we're essentially overwriting what was there before, right? That's the kind of idea. Because like if the key isn't in the map, then we create the new linked list node, right? And we assign it to the that kind of like we're assigning it into the table here, but we're not done. We need to actually add that node to our linked list. So how do we do that? We need to call the add node function on the new node. And the reason why we can do this, we could pass new node, or we could do self.map at index key. It doesn't matter, because they're all because new node is an object, and this is referencing the new node. So if we pass in the new node or we pass in this, they're both the same thing. So that's fine. So we add the new node. So how is adding the new node going to work? So we need to be able to add this new node in constant time. And the idea of adding a new node is we essentially want the LRU. So okay. Yeah, Yeah, so let's go back a bit. So if we're adding a new node, think of it like this. MRU and LRU are going to be pointing to each other, like next and prev. The new node, we need to basically get the we need a kind of way to get the next of LRU, right? So we need a way to get the next of this, right? And then we need to essentially put that new node before. So imagine there was a node here. Well, MRU is the node in front of it. So we essentially just want to get the node in front of it and kind of put that node and put this new node in between them. So how do we do that? So right, so to add a new node, we basically collect the next of LRU. I'll just call it next like that. Is going to equal to self dot LRU dot next. Right, I actually realized something. I forgot to. Okay, so the self dot LRU dot next is going to equal to self dot MRU, and the self dot MRU dot prev is going to equal to self dot LRU. So what are we doing? We're basically making them dangle across each other. The next and the prev of both of them should be empty. So now once we do this, we're basically going to get the MRU node, and we're essentially we want that new we want to kind of update the pointers. So let's think about this. To update the pointer, we store the next of the LRU in here, and we essentially want the LRU to now point to this new node. So this self.LRU dot next is going to equal to this new node, and the new nodes dot prev is going to equal to self.LRU and then right, and the nodes dot next is going to equal to next, and the next dot prev is going to equal to the new node. So what have I done? So basically, imagine there's no node here. So if there is a node, we're essentially storing the next, which is this node. We're saying that the prevs, the LRU's next is going to be that new node. The next node's, the new node's prev is going to be the self.LRU. The node's next is going to be the next node here, and the prev of that new node is going to be the new node that we've just inserted. That's essentially how add is going to work. But for remove, it's going to be a bit different. So for remove, yeah, we'll get to remove later. Okay, let's get into remove later. Yeah, because when you do insert the node, it's currently the least frequently used. When we're updating it, we actually want to remove the node. Remove node, which is going to be yeah, so if we are like updating it, that counts as using it. So we want to remove it and then add it again. Oh, I just realized I actually did the add node wrong. No, because the add is always going to be putting it on the LRU. Give me 1 second, guys. Let me quickly think, because this is just based on intuition, what I've learned. So I'm not really cramming anything. I want to kind of figure it out again. Just give me a second to think. Sorry. Okay, so the idea is still the same. We're actually going to switch this. So there's going to be MRU here and the LRU. Because yeah, so the most frequently used is actually going to be at the front here, right? Remove and add. I mean, it doesn't really matter how. It just depends on how I want this to work. And if it's not, then we add the new node, which is just going to be that doesn't necessarily, because because the way that I'm doing it now is that the new node goes in the front, or the least recently used goes in the front. But that's not correct, because now when I update the value, that does count as a use. So I'd want to remove the node and put it at the front. Yep. Yeah. Yep. So when you add a node, it is automatically, and then when you add a new node, LRU key was 2, evict 2. Okay, so it was kind of like the idea is we do 1 and then 2, right? And then we add 3. Yeah, because when we add 1, we add 2. We add 3. But we're kind of out of the limit, right? Right, but what was the node? What was the node before this, which is it's 2. So we kind of do remove it and keep it the same. We add 4. I see. So we add 1, we add 2, we get on 1, so get 1 comes here. We add 3, but we're kind of out, so we just remove that node. We get on 2, nothing's there. We add 4. But 1 is the one there, so we remove it. Yeah, so, okay, so kind of is the idea, right? So, yeah, so we add 1, we add 2, like that. So this is adding. We add 1, we add 2. LRU is going to be this. MRU is going to be this. Right? So we add 1, we add 2, we get on 1, so this actually gets removed. Yeah, we add 1, so this gets removed, and it goes here. Right, okay, so the add is wrong. So to add, we actually don't want to do that. Instead, sorry guys. So to add, we actually want to get the prev of MRU. Yeah, so want the prev. We want to say MRU the prev, not next. The node dot prev should equal to prev. Right, that should be node and prev. The node right behind MRU should be that, and then this prev node, its next should be the new node, and the prev of this node should be the former node, and then this node's dot next, and the MRU self dot MRU dot next dot prev is going to equal to self.mru, and this should be node, right? The new node that's getting added. That's the whole idea, right? So when we add 1, so the prev is going to be LRU, the prev.next, which is this, is going to be 1. The prev is going to be this node. The prev, the next of this is going to be this, and the prev of this should be this. That's correct. And then that's how add node works. So how should remove work? Remove should remove the element here. So right? So we kind of have this idea of 1, 2, right? And then when we get on 1, we kind of want to remove 1. So how to remove 1? Yeah, so how do we remove 1? We get the prev and next is going to equal to node.prev and then node.next, right? And then how do we remove it? We essentially want the prev.next to equal to next, and the next.prev to equal to the prev. So yeah, right? So yeah, so that's how you remove the node, right? So the next of the prev is now the next node, and the prev of the, yeah, so that's essentially removing the node. Yeah. That's the whole idea of it. Yeah. So I just realized I didn't even time myself. Really poor of me. Sorry guys. I'm not feeling well, so that's another thing as well. But yeah, so the idea here is now if that isn't there, we add it. So if it is, There we remove the node, and we kind of want to add the node again. Right? If we're getting the node, if the we kind of want to get the value, which is going to equal to self.map a key. We're going to return that value, but before we do that, we have to make sure we remove the node, which is going to be self.map. Right, that should be .val. Self.map a key, and then add the node again, which is self.map a key, and then we return that new node. Yeah. If you can note it out, we add the new node. With the value, sorry guys, so sorry about that. Wait, is this still going? Okay, it's still going. Yeah, so how am I doing this now? So if I do 1, 2, and I try to, that should be 2, 1 now, because remove it and then add it back again. Then we'll try to put 3. We can just add the new node. So we add it. Else the value is going to be equal to the value, and then we remove the node and add it back again, and then we need to get the length of this, the current size, which is going to be equal to the length of the self, the map, and if the size is greater than or equal to the self.capacity, we kind of want to remove the node at the LRU.next. So we'll say remove excess node is going to equal to the self.lru.next, and then we're going to do self.remove node on excess node. I think this is all. I might have made a lot of mistakes. Is it called add node? Right, because, oh, do I have to like, okay. Wow, I haven't used Python in some time. So I'll literally need to call self dots on all of them. Right. Okay, I think that should be. Okay, so we are wrong. What are we doing wrong here? So, we get 2 instead of -1. Why? So, ours returns 2. Let's see. So, how is this working? So we put 1. We put 2. We get 1, so that becomes 2, 1. We put 3. Okay. So we get 1. We put 3, so that becomes. We get 2, or we still get 2 here? Oh, because we need to actually delete the, right, delete the self.map index key, right? Index, so yeah, we need to actually store the key at the node because we need to actually delete that. So we need self.key is equal to key, and then we're essentially removing the excess node.key. So that will essentially remove right, so we want to pass -1 here, -1 here, and then when we're adding the node, the new node, we need to actually pass in the key in here as well. Okay, so we are getting -1 again. Right. So what am I doing here? Wrong. When we try to get on 1, that deletes it. Why? I think it's when it's greater than, maybe? When it's greater than the capacity. So I was deleting it when it was exactly 2, but it's still fine. New node. Cannot access. Oh my god. Yeah, self.map NX key. Yeah, because that's going to be the new node, basically. I think that should be the entire solution. Yeah, that took me a lot of time, actually. I'm going to actually check how long that took me. But, yeah, how do I... Okay, I'm going to explain the idea. So, this is a lot of code. The idea is we're trying to, like shift nodes in constant time. So we have these 2 nodes here, which are like our edge pointers, like edges. I don't know how to explain it, but yeah, this is our least recently used and our most recently used node. When we add a node, we're essentially adding that to the least frequently used. When we add a node, we're essentially adding it to the most recently used. Yeah, when we add a node, we're essentially adding it to the most recently used, which in this case would be 1. So we add 1 in here. When we add a 2, 2 becomes the most recently used, and 1 goes to the least recently used. When we add 3, 3 here, it's fine. It becomes the most recently used, but because we're out of capacity, 1 is the least recently used here. So we're going to remove 1 from the map. Which is using the LRU.next, because the LRU.next would always be pointing to the least recently used. I just like the idea of it. Yeah. Let me know in the comments if you guys have questions about this. I don't know, like most of it was me even trying to like think about the solution, because yeah, this wasn't even auto memorization or anything. This was literally just me understanding the intuition about the problem. But yeah, it was just me making some silly mistakes and then that. But yeah, let's go on to the next question, because I did say I was gonna solve more. So that is, I'm not gonna be doing the hards. I will get to these later on. But yeah, let's go into the trees. To be honest, I think this is gonna be really short. Most of these problems, like, I'm really really quick with trees. Like trees is like one of my favorites. But yeah, let's let's solve this. So we are given the problem invert binary tree. So now we're getting to the tree section. There is going to be a lot of like recursion. A recursion is when you call a function inside itself. Sorry guys, not feeling well. So given the root of a binary tree, invert the binary tree and return its root. So the idea here is that we want to kind of flip the references. So the left becomes the right and the right becomes the left. So yeah, so if there isn't a root, we kind of just want to return none, because there isn't anything. When was the last time I did this problem? Did August? Okay. If there isn't a root, I return none, right? Like there's nothing to even reverse. If there is something, then we essentially want to flip the left and the right, right? So we want to say the root dot left and the root dot right equal to the root dot left and the root dot right, right? And we want to do this for all the other children. So we're going to say self dot invert tree. The same problem we solved at this case where we swap them, we kind of want to do them in here as well. So we're going to say root dot left and self dot invert tree, root dot right, and then we kind of just want to return the root after, because basically what we've done here is that this function gets the root, which is 4. We basically say the left is going to equal, this should actually be the right and this should be the left. We're kind of flipping them, so the left becomes the right and the right becomes the left, and then we're calling the same function again on the left node as the root. So we're doing the same thing again at this level. This will kind of flip, the left becomes the right and the right becomes the left. They do the same thing on the, and it will actually call, because the DFS, right? So it will actually continue calling on the left here. Well, it does the root dot left and root dot right. There's nothing there. Check on the left here. The left doesn't have anything. It will return back. It will call on the right. There's nothing. It will come back up. It will come back to 2. 2 will call on the root dot right. It will flip. Has nothing, and it's kind of like it's DFS, right? So it's traversing one path and then solving kind of like going back up and then trying another path, and yeah, that's kind of the idea of the solution. Kind of simple. Let's not spend too much time on that. Let's try and go to the maximum depth of a binary tree. So this will be the last one I'll do for today. I do need to go get some more rest because I'm honestly not feeling too well. And yeah, let's quickly get it done. So this question wants us to find the maximum depth of a binary tree. Okay, so there is multiple ways you can do this. So we do want to like find the maximum depth. So we are starting with the root node here. We kind of want to go to the left. If we can go to the left again, we continue going. Right again, we keep on going. The same thing here. So kind of the idea is if we are kind of ask our children, I essentially want to do if there isn't a root, and then we kind of want to return 0, right? That's kind of the idea, right? So sorry, if there isn't a root, then we kind of want to return 0. If there is, right, the left and the right, so we essentially want to ask our left child, hey, what's the biggest you have for you, right? Right, so our left is always going to be equal to the self.max depth of roots dot left, right? Because we're basically going to ask our child is going to come down here, it's going to go on the left again. This is going to return 0, but I want this to return 1. So I want to actually, we're going to do max of that plus 1. So it's going to go down to this, it's going to have nothing, it's going to return 0. At this point, we now want to return 0 plus 1. This will return 1 up here. So we know that the depth of this one is 1. And the same idea is for the right. So we're going to go on the right here, it's going to go on the right. Right, so it's finished explaining the right. So the right will come in here. It's actually going to the left here. The left is going to go down again. This is going to return 0, right? This is going to be 0 plus 1. It's going to return 1 here. So the left here is going to be 1 plus 1, which is going to be 2 at this point. And this is going to go, right. No, sorry. We go left, right? This is going to go to the left again. It's going to return 0. This is going to be 0 plus 1. It's going to return that. So the left here is going to be 1, which is correct. The right here, we're going to go right? And then when it goes to the right here, we're actually going to go to the left, right? So it's going to go, it's going to come here. There's still a left, so we go to the left. Let's go to the left here. There's nothing here. Return 0. So this becomes 0 plus 1, right? Which is going to be 1. It returns here. So the left of this one is 1. It goes to the right. There's nothing here on the right, so it returns 0. This is going to be 0 plus 1, so it's going to return 1. So this is going to return 1 and 1, and then this is going to return these two are going to be 1 and 1. So the left and right should be 1 here, and we kind of want to return 1 up here, right? So we want to return 2 here. So we're actually going to return, but which one do we collect? We kind of want to collect the max one. So we want to say max depth is going to equal to the max between left and right. And we kind of want to return that, because whichever one does return the maximum, we kind of want to return that plus our node. So we kind of want to return max depth plus 1. Well, that's kind of the idea of it, right? Because this will both return 1, and we will return 2. Oh wait, so this will return, right? This is going to return 1, 1, 1. For the next max of both of them, that's 1. So we return 2 here. So this is going to be the max of both of them, which is going to be 2, and then we return 1. That's like the main idea, but we're getting 6 here. So I thought this was going to be quick. Okay, so right, so we go left, that returns 0. This returns 1. So at this point, this is actually going to be 0. This is going to be 1 and 1. So the max between both of them, this is actually going to return 2. So sorry, this should actually not be plus 1. This should be, because this is going to return 1, this is going to return 1, and what I'm doing here, both of them are actually, this is going to return, yeah, so it should just be max depth. It should just be 0, and then that would return plus 1. I think that's more correct, yeah, because I was over counting there. I was over counting. But yeah, that's it for today. I will record another one tomorrow. Sorry I haven't posted in a while. A lot has been going on. Kind of the schoolwork is like really on my mind. So yeah, I'm gonna continue doing that. I will be trying to post more going forward. And yeah, thank you guys for watching. If you have any more suggestions on what I should record, what I should post, please let me know in the comments. And hope you guys have a blessed day. Remember to pray, and yeah, wish you guys the best day ever. And yeah, I'll see you guys in the next one. I'm gonna have to go rest now because I'm not feeling too well. But yeah, see you guys.